This video will be on section 12.1, logarithmic functions. This section, it looks like there's quite a bit. There is, a lot of different topics, but as we will see, they're not too deep since this is an introduction. So first we'll see what is the definition of a logarithmic function. We'll actually see that it's related to an exponential function. It's going to actually be its inverse. So one thing that's going to be important is being able to interchange between exponential and logarithmic form, which we'll see what that means. Then we'll want to be able to evaluate logarithms on a calculator and using the change of base formula. Then we'll look at the basic log graphs, and really the last two bullet points go along with the graphs, determining the domain and vertical asymptote of a logarithmic function. It'll always have one of those. And then lastly, how to actually determine the graph of a logarithmic function. Right, so, once again, a lot of little things, but it's not too terribly much. All right, if you're new to logarithms, one thing I would definitely say is take your time with this section. The homework is one of the longer sections of homework as far as the number of problems, but once you get the hang of it, you can do them pretty quickly. Right. So a basic logarithmic function f is written as f of x equals log base b of x. Right, so b, as I said, is called the base. And you'll notice that it has going to have the same condition as the exponential condition. The base must be positive and it cannot equal 1. Now, there are a couple things that I like to point out here about a logarithmic function. Logarithmic functions, whenever you write log, it must have a base. So b will just be representing some number and an input. So that means you cannot write just log base b. You have to have log with a base and also something inside. Okay, so we'll actually see when we look at the calculator problems that if you type in just log without an input, it won't give you anything. It'll read it as an error. Okay. All right, so a couple notes here. The log function, log base b of x, is the inverse of the function b to the x power. Well, actually, this is a definition. This isn't something you can prove. It's just the definition. The domain, because it's the inverse of the exponential function, you actually switch the domain and range of the exponential function because we switch x with y. So the domain of the log function is 0 to infinity. What this means is you can only have positive numbers inside a logarithm regardless of the base. So it doesn't matter if the base is 1/2 or 5 or anything that's valid. You must have a positive number inside. One thing that's usually can throw some people through a loop when you solve equations with logs, which we'll see in a later section, is that because the range of the log function is negative infinity to infinity, all real numbers, it can equal anything. It can come out and spit out a positive or negative number. So logs can equal a negative number, but must be positive inside. All right, so even though we haven't actually written a log example yet, there are two examples that are very special in as far as logs go, two special bases. It's log base 10. When we deal with log base 10, very often you will see no base written, and it's understood to be 10. Right? It's not that there's not a base, it's just base 10. Okay. Now, the other special one is when the base is e. It actually looks like a totally different thing. It says log base e of x, we write as ln of x. So base e is equal to the natural log. That's what ln stands for. So this is called the natural logarithm, and the way you say it is ln of x because it's, it's ln for log and natural. Right? I guess, the way most languages work is they would put the log, what's it called, the noun before the adjective. But this is an English class, so we don't need to worry about that. All right, and this is just another reminder of what I just wrote. You cannot have log with a base without an input. So log base b makes no sense without an input. You will not be able to divide by log because, once again, it's not anything. It means nothing. It's like dividing by a square root symbol. You can't do that. You get rid of square root symbols by squaring each side. And the other thing, the x or whatever is inside the parentheses is attached with the log base b. I'd like to mention that now because when we end up solving equations with logs, it's very important that you don't try to do something you can't do. All right, so one thing that's very important is interchanging between exponential and logarithmic form. Basically, what we have here might not make sense. If we write log base 4 of 7, which we'll talk about in a minute, what does that mean? Well, you can actually interpret it by switching between log and exponential form. So the left side here is called log form because it has the log written, and the right side is called the exponential form because we have an exponent. And what's important is to be able to switch between the two. Right, so the way to switch is much more visual than you should just memorize this formula. It's much more visual than that, and it's a lot easier if you visualize it. All right, so it's much easier to visualize. The way I think about it, notice that the base is the same on each side. Meaning when we practice this, if you know the base of the exponent, as we would in this problem, I already know what the base of the log is going to be. And then if we have log form and we want to switch to exponential form, we already know what the base is going to be. Also notice, let's say we want to go from log form to exponential form. Well, what we're doing here is the b is with the x on log form and the b is with the y on exponential form. So think about moving the base to the other side. And, if the b comes over here, we get rid of the log, and that's exactly how we can make this. If the b comes over here, we have b to the y power equals, what's left is just x. But it actually works exactly the same way if we go back the other way. If I'm in exponential form and I want to get over here, right in this side, the b is with the y. And if I want to get it to this form, the b is with the x. So I do the same thing. I move the base to the other side. And then the only other thing you have to remember is if you don't have a log, like we in this one, then when we get the log form, we would have a log. If we do have a log and we want to get the exponential form, we get rid of it. So we add or remove the log appropriately when we switch sides. And this is going to be important because this is one of the ways you can actually solve log and exponential equations. But what we're going to do is just practice switching for now. So this first one says e to the x equals 4, and we want to write the equation in logarithmic form for these three. So I want to do exactly what I visualized. Grab the base, move it to the other side, right? So when we move the base to the other side, what's over here on the left? Well, the e's gone, so just x. And now when we move the base to the other side, since we were starting with an exponent, we're going to get a log. Its base is e, and the inside is 4. And this is one of our special logs, so it's good to practice writing it in the more appropriate term. Since log base e is the natural log, we want to simplify it. And we get x equals log base e is the natural log of 4. Now, one thing that's important about these problems is it wants the equation, so you got to type this whole thing in. Don't just type in ln of 4, don't just type in x, you need to type in the entire equation. Right, but we're going to do the same thing for the next two. So number 2 here, we got 10 to the b equals t. Take the base, move it to the other side. Then what's left on the left side is b, and what's on the right side, the 10 becomes the base of the log, and we have the t inside. And this is another one of our special logs. When we have log base 10, we just omit the base. So our equation would be b equals log of t. Same thing, type in the equation. All right, in the last one, we have 9 to the t equals p. But we're doing the same thing. We're moving the base to the other side as the base of a log. The left side is now t, and the right side we get log base 9 of p. And base 9 is not a special base, so we got to leave it like this. Okay. But if you can do it this way, you can actually do it the other way, just the same, but opposite. Right, so the following three we want to express in exponential form. We're starting in log form. But we do exactly the same thing. We grab the base and move to the other side on all of these. So the first one here, we have our base of t, we move it to the other side. Remember, we're switching to exponential form. Since we start with a log, it's going to go away. The left side's just what's inside here, which is b, and the right side has base b to the u power. And same thing as before, you want to type in the whole equation, don't just type in one side. All right, so number 2, we have log of v equals 4. Remember this, with the log without a base, has an invisible 10. And it's usually helpful to just write in so you can see it. But we do the same thing we did for the other ones. Grab the base, move it to the other side. The only thing that remains on the left side is v, and the right side is 10 to the 4th power. Now, one thing I think that's kind of funny about these is, the way this one is, this is just a number, but you still want to type in the equation. So don't simplify 10 to the 4th. And then the last one, ln of y equals 2. ln, that's our natural log, it has a base e. But we do the same thing. We take the base, move it to the other side, and we get y is what remains on the left. And on the right side, we get the base is e and the exponent is 2. And same thing as before, this is just a number, e to the second power, but don't simplify any of these. Write the entire equation. All right, now one thing I'd like to just mention now, even though we're not going to do this for a couple sections, is that if we were solving for v here, or if we were solving for y here, this is exactly how we could do it, because we have v equals and we have y equals. So even though we haven't solved a logarithmic equation, this is one way to be able to do it. All right, now we will look at the next topic, which is evaluating logarithms on the calculator and the change of base formula. Right. So the first thing, I like to just write down the change of base formula, because once we start using the calculator, then we can just not have to introduce a new formula. Right. So the reason a lot of calculators, not all of them, but most calculators can only evaluate base e or base 10 logarithms directly, meaning, and I go ahead and show you on most any calculator, you'll see a log button and you'll see an ln button, but you won't see a log with a base b button. Some calculators have a hidden button for that, some do not. And if you want to evaluate something that's not log or ln, like number 4 down here, you have to use the change of base formula. So what the change of base formula says is this: a log base b of x, it's equivalent to all three of these. So the first one says log base c of x times log base, or divided by log base c of b. Now what this is saying is you can change the base to anything as long as you make the inside top, the original inside, and the inside on the bottom the previous base. The one I like to remember the most is the one at the end here, ln of x divided by ln of b. So when we get down to that last problem, what we're going to do is use this formula. We're going to do ln of the thing inside divided by ln of the base. Right. Now you can use just log. The reason I prefer ln instead of the log one, it doesn't matter which one you choose, but we have a lot of log rules going forward, and so this might look and cause some confusion with the log rule, but there's no ln rule, so to speak. So this makes it look totally different. Right, so first one, the first three actually we'll be able to do on the calculator. It says evaluate the following logarithms and evaluate to 4 spots when necessary. So the first one is ln of 0.003, and the answer is negative 5.8091. Remember, I mentioned before at the beginning that the logs can equal anything. What comes out can be anything, positive or negative. So there's nothing weird about that. Now the second one is ln of negative 0.008. And if you remember something from before, the inside of the log has to be positive. So this is D and E. We cannot plug in 0 or a negative number. It has to be positive. Right, so even though it's not in the questions here, just to reiterate, if you try to do ln of 0, if you put 0 on the inside, it's also an error. It's not a number. All right, so number 3, log of 8. You have to make sure you hit the log button instead of ln. And we get 0.9031. Right, now one thing I just want to do real quickly is if you do hit the ln instead of the log, you will get a different answer. So be careful on that. Really what this number is telling you is it's telling you 10 raised to this power is what gives you 8. If you have base e, then it's going to spit out e raised to what power gives you 8. And e and 10 are different numbers. All right, so the last one is one that we have a base that's not 10 or e. And for this, either you know where the different base button is on your calculator, which some of you will not have anyway. So we got to use the change of base. We get log of 0.84, log with base 0.84 of 12.75. Like we mentioned before, the change of base formula tells you to do the ln of the inside divided by the ln of the base. So this equals the natural log of 12.75 divided by the natural log of 0.84. And this is what we type in our calculator. Now, one thing I will say, and I'll show you with the calculator, is if you type it in any differently at all, cancel out the ln's, try to put them in one ln because it's not the same on the top and bottom, you will get it wrong. So you must type it in exactly like this. We got ln of 12.75, oops, close the parentheses, divided by ln of 0.84, and we get negative 14.5998. Now, like I mentioned, if you type this in another way, it's wrong. If you make it one ln, so ln of 12.75 divided by, let's see if I can hit the 5, divided by 0.84. Very different number. If you think you can cancel the ln's out, you can't, because if we divide these two numbers, we'll get a very different number as well. Right, so you have to leave it like this. There is not another way. Now, if you do log instead of ln, that works too. But as we saw before, log and ln are not the same. It's just that with this rule, you can use either one. You get the same number. But don't mix and match. All right, so our log graphs. Log graphs are similar to exponential graphs in the way they're shaped and because they're inverses. We will have two pictures like we did with exponential graphs. We'll have one when b is between 0 and 1, and one when b is bigger than 1. And you'll actually notice it's very similar when we look at what's the difference between the two. All right, so the first thing, the very important defining characteristic of log graphs, especially the basic one here, is that there is a vertical asymptote at x equals 0, which is the same as the y-axis. And that's the same for both. Right. Ultimately, what it's going to be is you get a vertical asymptote when the inside is 0. So if we shift the graph left or right, it could change that. Now, since we don't really have log rules like we do exponential rules, one thing we'll go ahead and mention is that you do have an x-intercept at x equals 1. And for the x-intercepts, we know that y is 0. And that's for both of them as well. Right, so what is the case is if the inside of the log is 1, the output is always 0. It doesn't matter what the base is. And I can just show you with ln and log. If we type 1 into each, they are both 0. Right. Now, the main difference is very, very similar to exponential graphs. When you have the base between 0 and 1, it's a decreasing graph, and it looks like this. If you turn your head, you kind of see an exponential graph where this was the horizontal asymptote, but it's just flipped on its side. So that's the main characteristic, is this is decreasing, and when the base is bigger than 1, probably already guessed it, it's increasing. So if you pick any base that's between 0 and 1 and graph it, or if you pick a base bigger than 1 and you graph it, it'll look something like this shape. I'll do the one bigger than 1 since it's very common to look at just the graph of ln of x, since that base is e and e is bigger than 1. So I'm going to graph ln of x, then zoom in 6 to put in the standard window. What happens here, the reason why the graph looks cut off, is the vertical asymptote, it gets so steep that it can't actually draw it in. So there is an invisible vertical line here. But it looks something like this shape if you could imagine flattening this out next to the y-axis. Right. Now, as far as graphing logarithmic functions, we're not looking for as much detail as exponential graphs. We're going to really look for two things. What is the domain / vertical asymptote? It's kind of the same question. And also, what is the nature of the graph? Is it increasing or decreasing? All right, so as I have written down before, we already mentioned this. The domain is 0 to infinity. It doesn't touch 0 because of the vertical asymptotes. That's why we got parentheses. The range is all real numbers. What that means is this graph goes up or down forever, and this one goes up forever and down. We have a vertical asymptote of x equals 0. In general, the numbers that make the inside 0. And then it's increasing if we have b bigger than 1, decreasing if b is between 0 and 1. Right, so we'll first work on the domain and vertical asymptote without graphing, and then we will look at a couple graphs. All right, so determining the domain and vertical asymptote of a logarithmic function, it's rather straightforward. Notice, the vertical asymptotes are where the inside's 0. The domain is where the inside's bigger than 0. So what you do to get the domain, determine the domain of a logarithmic function, we set the inside greater than 0. Remember, not greater than or equal to, it's a little different than the square roots, and solve it. And to find the vertical asymptote, we set it equal to 0 and solve that. But as you'll see, if you do the domain, that number that pops out is also the vertical asymptote. But you want to do domain first, then get vertical asymptote. One thing some of the questions like to ask is, what is the range of the logarithmic function? Unless you have a really, really weird one, which we won't see in this class, the range is always negative infinity to infinity. Because we talked about before how we generally don't ask that question for functions, the range, but this is one we can answer. All right, so we got y equals log of 2 minus 5x. We want the domain in interval notation. the domain in set builder notation, and then the equation of the vertical asymptote. All right, so let's do the domain first. We set the inside greater than 0. 2 minus 5x greater than 0, and solve for x. Right, so we can subtract 2 from each side. We get negative 5x is greater than negative 2. And then to get x by itself, we divide by negative 5. And we know when we divide by a negative number, we have to flip the inequality. And we get x is less than, the negatives cancel out, 2 over 5. Now, even though it's the second thing that's asked, this is the set builder notation. Right, because set builder is really the same thing as inequality notation. It is, this part's filled out for you, and the part you're going to fill out is x is less than 2/5, the inequality you get. Now, if we want interval notation, you can draw a number line, mark off our number here, 2/5, and because it's less than, not equal to, we have an open circle, and to the left, less than is smaller. The interval there starts at negative infinity, nothing stops us from going back, and it goes all the way up till 2/5, and we get a parentheses because it's an open circle. Right, so that's the domain, and when you find the vertical asymptote, all you do is set the inside equal to 0 and solve it. Now I'm just going to go through it, but you'll see that this 2/5 will pop out. So we got 2 minus 5x equals 0. We would solve it the same way here, but we don't have to worry about inequality. Subtract the 2 from each side. Got negative 5x equals negative 2. And divide each side by negative 5. And we get x equals, the negatives cancel out, 2/5. But if you remember from before, we had a previous section with vertical asymptotes, you have to write the x equals part, not just the number. All right, so that's how we find the domain and vertical asymptote of a logarithmic function. The next and last thing in this section is if you're given a graph now, how do you figure out, or if you're given a function, how do you figure out the graph? Well, you really do two things. Determine the domain in vertical asymptote. That's the first thing, that's what we did above. And then from the base, determine whether the graph is increasing or decreasing. If you do those two things, these questions are multiple choice and you will narrow it down to one. Right, so number one here, you see the four graph choices. It says choose the graph of y equals log base 1/4 of x plus 5. Now you can do the domain or the vertical asymptote, it'll be good enough. And the vertical asymptote is just easier to do because you don't have to worry about the inequality. So for the vertical asymptote, set the inside x plus 5 equal to 0 and solve that. And our vertical asymptote is at negative 5. What you can do is just narrow it down a little bit. The vertical asymptote, if you drew in, this one's going to be about right there. That one's going to be about right there. And you can see these are both at 5, x equals 5, not negative 5. If it's really small, just, you'll be able to see it bigger on your paper, but the negative 5 would be on this side somewhere. So those are both going to be wrong. They don't have the correct vertical asymptote. And if you look at the vertical asymptotes on this one, the two on the right here, they are both correct. So we need another way to figure out which one it is. And that's why we need the increasing or decreasing, and that comes from the base. Since the base here is 1/4, this is less than 1, which means it's decreasing. All right, so that leaves us with this as our answer choice. This one is decreasing as we move to the right, it's going down. The one down here is increasing, so it's no good. All right, so if you look at those two things, you will narrow it down to 1 and you'll be good to go. All right, so the next one here, this is one that I really just want everyone to be careful on. Choose the graph of y equals log base 6 of x minus 4, and you'll notice the minus 4 is on the outside of this one. It's not on the inside of the parentheses. So when we do the vertical asymptote here, we set the inside equal to 0, but the inside is just x. It's not x minus 4. Right, and so that means the vertical asymptote is the y-axis for this one. The two on the right are both incorrect. This one has vertical asymptote -4. Actually, both of them do. And that's why they're trying to mess you up with a -4 here. So it doesn't match that. But once you get the vertical asymptote down, once again, just look at the two choices remaining and you'll be able to narrow it down by the base. Since the base here equals 6, which is bigger than 1, it is an increasing graph. And that is the one on the top left. The bottom left, this one's decreasing. That one's no good, but the one on the top right is good. All right, so that's just something to be careful on when you're choosing these. The parentheses, what's inside it, is what matters. If you have a number on the outside, visually it actually moves the graph up and down. This one moved the graph down 4, but you don't need to necessarily remember that for this problem. You just need to remember it's on the outside so it doesn't take part of the vertical asymptote.